The first half of Chapter 9 deals with thermodynamic modeling of internal combustion engines. Now, I'm going to have to admit to you that when I was a student and then continued through the rest of my life, um, I did not and do not have a burning interest in becoming an expert in internal combustion engines. I was my dad did the best he could to describe things about internal combustion engines to me, um, and I'm afraid to admit that I didn't just pick up on that and didn't become a great car enthusiast like many mechanical engineers are. But there's something very powerful about modeling the performance of internal combustion engines, even if you're like me and you didn't have this burning desire to be an automotive enthusiast. So let's see what it takes to set up a thermodynamic model for any type of internal combustion engine. And so here's a cutaway of a classic internal combustion engine. And let's see, what have I got on this slide? I've made a screenshot of section 9.1, introducing engineering terminology. And that is going to be important. And even with my lack of burning interest, at least my dad was able to communicate to me, what does top dead center mean? What does bottom dead center mean? And some basics of that. And he also did his best, uh, may he rest in peace, to describe to me the four-stroke engine cycle. And so recognize this is a mechanical cycle. And he just did a great job of very patiently explaining to me, well, in the first is we've got an intake stroke where we go from top dead center, as shown here, to bottom dead center. Bottom dead center will be when the crank is all the way down as low as it can go, where we bring in air, we bring in fresh air. Then there's a compression stroke from bottom dead center to top dead center that compresses that air. Okay. At that point, there's some type of combustion, internal combustion in there. Something happens so that the pressure goes way up in that what's in the gas that's compressed with the fuel. You get combustion, and that's what enables us to do the power stroke, moving towards the bottom dead center. That's what gives us the engine power to drive our cars, to drive our vehicles. And then, as my dad explained, then we've got to exhaust that gas. We've got to exhaust the exhaust gas to start all over again, to bring in fresh air, to add fuel, to begin the combustion process, and on and on. So there's an exhaust stroke for that would be a mechanical cycle. And so please do recognize, especially for those of you car enthusiasts, I think it's wonderful that there are many mechanical engineers that they would devote their lives to internal combustion engines. That's great. But recognize that that is a mechanical cycle. Okay. What we want to do is to create a thermodynamic cycle to be able to describe the performance of our internal combustion engine. And so there are some folks that are watching this video that know a lot more about internal combustion engines than I do, but at least at a minimum, so we're still in section 9.1, you realize that there may be a spark plug involved. That would be for a spark ignition, like a gasoline engine, but also there are diesel engines that don't have spark plugs. They have fuel injectors, and there's key differences between a diesel engine and a gasoline or spark ignition engine. And we're going to want to create thermodynamic models of both of those. But in our thermodynamic model, recognize what we're going to do is we're going to model the air inside this piston and cylinder as a closed system. So that's different than the mechanical cycle. So that's an important thing to pick up. But still, we're going to kind of keep some of the jargon from the real honest to goodness engines. Things like top dead center. That's where the volume is a minimum of the air. Bottom dead center. That's where the volume is a maximum. But we're gonna say that we're modeling a closed system that's full of air. So I'm going to suggest that you're already good at analyzing pistons and cylinders. By golly, you think, man, I've had a hell of a lot of practice involving problems that involve pistons and cylinders, and that is true, and that's going to be our starting point in Chapter 9. So you're already good at analyzing processes associated with pistons and cylinders. That's going to be the basis of our thermodynamic models for internal combustion engines. Now, this has made me think back about my student days. And this pressure volume diagram, even though I didn't use the textbook that you're using, the textbook that I was using as a student, it had nearly exactly the same sketch of the mechanical cycle in terms of pressure and volume, where this kind of crazy looking process modeled the compression stroke, the power stroke, the exhaust stroke, and the intake stroke. So recognize that this PV diagram is not a thermodynamic cycle. It's sort of depicting a mechanical cycle. That's not what we're going to do computationally. Our job is to model this sort of real process with a thermodynamic closed system thermodynamic model. So now what I want to do is summarize jargon that's presented in your textbook. In other words, I'm trying to pick out the key points that your textbook is trying to make. So top dead center. So do you see that at top dead center, where the piston is as close as that can be to the intake and exhaust valves and or spark plug or fuel injector, that's going to represent the minimum volume. V minimum corresponds to top dead center. Okay. That's called the clearance volume in your textbook. That's going to be mentioned in your homework problems. Clearance volume given a number, that's V minimum. The maximum volume, that's going to correspond to bottom dead center. So I think you can visualize that with the sketch. When the piston is as far as it can go towards the crankshaft, that's going to be bottom dead center, correspond to V maximum. The displacement volume in your textbook. The displacement volume is simply the difference between the maximum volume and the minimum volume. So there will be homework problems where the assignment is calculate the displacement volume. All you got to do is get values for V max and V min and subtract the two. Displacement volume. Compression ratio. This is a term that my dad tried to explain to me, and I wasn't very good at absorbing it. But once I got into thermodynamics class, I got a better feel for it in terms of the definition of compression ratio, little r. Little r, compression ratio, and that is simply the ratio of volumes, V max divided by V min. So obviously it's going to be some number bigger than one. It's going to be kind of potentially a large type number, 6 or 7 or 8 or 12 or 20, okay, depending on the type of engine, okay. But do recognize that the compression ratio has nothing to do with pressures. It's a volume ratio. So that is, and so the compression ratio R is fixed by the mechanical design of the engine, the top dead center position, the bottom dead center position, and the stroke dimensions. Okay, so that's an important thing to remember as you're working through your homework problems. Now, this is a term that I had never heard of until I got into thermodynamics and then later in our senior level mechanical engineering courses. This is a term called the mean effective pressure of an engine, MEP, mean effective pressure. And I'm going to have to admit, since I'm not a car enthusiast, that I have to go back and refresh my memory on this definition nearly every time that I'm asked to determine the mean effective pressure of an internal combustion engine. It's in your text. Here's a clip from your text. Mean effective pressure is net work for one cycle divided by the displacement volume, V max minus V min. Okay. And that's in terms of a formula, it's W net in kilojoules divided by the displacement volume, V max minus V min, which is cubic meters. Well, let's do a unit check. What's this kilojoules per cubic meters? What is that? Well, a joule is a Newton meter. Okay. Oh, so now I can do some cancellations. So I've got kilonewtons per square meter. Oh, so the mean effective pressure units in SI are going to be in kilopascals, kPa. And you can go through the same drill if you're in English units. The units for mean effective pressure are going to be PSI, pounds per square inch. So what is a thermodynamic air standard cycle? I want to try to summarize your textbook material. Okay, hit the key points of your textbook material. So what are the basics of an air standard thermodynamic cycle? Okay. First, we've got a closed system model. We're going to analyze our cycle as if we've got a fixed mass of air contained within the piston and cylinder. So we don't have intake and exhaust. We've got a fixed mass of air contained within a piston and cylinder. Okay. I talked a little bit about the combustion process, right? So all internal combustion engines, there's combustion going on. For our thermodynamic model, we're going to model that combustion as adding heat, QH, from some high temperature heat reservoir, TH. So that's going to be a model for what's going on in the real world. And I'm going to tell you that the model's going to be pretty good. All right. Finally, instead of an exhaust process, we're going to model the exhaust process as a heat rejection model, where we're rejecting QL, let's say in kilojoules, down to the surroundings temperature at TL. And then finally, for our thermodynamic model, for all our internal combustion engines, for chapter 9, all our processes are going to be considered internally reversible. So in other words, no unrestrained expansion and no friction between the piston and cylinder. And that's going to turn out to be a fairly good model. So please be aware of that. Let me repeat this slide. For our air standard thermodynamic model, we're going to have closed system, heat addition instead of combustion, heat rejection, QL, instead of exhaust. And also for each process that we describe, each one of them is going to be considered internally reversible. And so that gives you an idea. That sort of gives you an idea of where we're headed for internal combustion engine cycle modeling. And my claim is you've had so much practice with pistons and cylinders, you're already pretty familiar with doing the computations associated with these models. Okay, so as you see, we didn't crunch any numbers. We didn't write down formulas very much. So in the next one, we are going to talk about starting with a specific model for a specific type of internal combustion engine. I hope that helps you get a feel for where we're headed and think about, man, there are some fundamentals here that I already know, and I've already got some experience and practice with.